Hallo, goedemorgen allemaal. Hello, good morning everyone, and welcome to the final day of Devoxx. I'm very excited to be here. I'm Jeroen Mols, I'm a GTE for Android, and today I want to share my experiences building connected products over the last 6 years. I currently work for a small company called Philips on the biggest and most exciting IoT system in the world, Philips Hue. I'm actually the lead Android developer there. And what I'd like to share with you today are lessons learned in general building connected products. I've built many other products. Many of the things Hue actually also adopts in their system, but this is by no means like a summary of how Hue actually does things. Now, I'm quite active on Twitter, so if you're also on Twitter, feel free to follow me at Molsjeroen. So, let's get started. The general theme of the presentation today is going to be that having code that works just doesn't cut it anymore. Apps, or applications in general, are getting more and more complex every day, which means that the cost of throwing away the code increases, so the likelihood of that decreases, so you're going to have to deal with the legacy code that you write for a longer amount of time. And I want to share with you today how that's actually applicable to IoT. So, what is a connected product? Well, let's build a product. Any product that you nowadays build has at least some kind of software in it. So even a speaker, it has some embedded software. But yeah, this is not a connected product, obviously. For that, we need to connect a smartphone. And then connecting a smartphone makes things more interesting, because suddenly you're using a Bluetooth connection, either standard Bluetooth or Bluetooth LE, but that connection already introduces quite a few points of failure, especially on Android. Yeah, a Bluetooth LE connection really is poorly supported by Android devices. But this setup has one big disadvantage, and that is that the product itself isn't connected to the internet all the time. It's only connected when your phone is connected. So therefore, it's probably interesting to move to a Wi-Fi connection. And then you may say yeah, but Wi-Fi is the most normal thing in the world. Why would that be different? Well, actually, most people don't buy a Wi-Fi router. They just get one from their mobile carrier. And the hardware they get typically isn't the best one of the bunch. So yeah, a lot of those devices are either very slow or don't support mainstream technologies like multicast. So this does actually introduce a significant point of failure. But yeah, having only Wi-Fi, okay, then you can control your product when you're at home, but you also want to do that when you're out of home, so you need to introduce your own backend server, and then stuff gets really interesting because you need to dynamically swap between routing all of the traffic over the Wi-Fi network or over your servers. So this makes stuff a lot more interesting. And then there could also be a good reason for you to actually add an extra item to your system, which is a bridge. For Philips Hue, we actually need a bridge, because our lamps, they use Zigbee, which is a mesh network, and your phone obviously cannot speak Zigbee. So we actually use a bridge, which bridges technology from Wi-Fi to Zigbee. But there's many other reasons why a bridge could be interesting. For instance, this is like the central brains of your system. So you can completely upgrade your system without having to replace all of the other hardware. It also facilitates the security for us, it simplifies the setup, and because it's an always-on device in your house, it allows you to do home automation routines, so time-based use cases. Now, when you start building a system like that, hopefully you gain some traction in the market, and then you're not going to stick with one product. So you add an extra product, which could either be a similar thing, like a radio, or something completely different, like some kind of control device. So you have hardware diversity to deal with. But it doesn't really stop there, because the hardware diversity could also start on the bridge side. For instance, at Philips Hue, we wanted to support Apple HomeKit, but in order to support HomeKit, you need to have an Apple-certified chip in your product. And turns out, asking customers to solder a chip onto their existing product isn't really user-friendly. So we had to ship a new bridge. And on the input side, you can support different use cases like smartwatches, cloud-to-cloud integration, Amazon Alexa, Google Home, game consoles, you name it. It could literally be anything. Do you already see what I'm getting at? Stuff gets very, very complex very, very quickly. And then to put things into perspective, this isn't near close to the complexity that Philips Hue has, because we don't have 3 different products. We have 40 or 50 of them. And every single point in this system is software updatable. So you can have software version mismatch across the entire board. And then not all devices are main powered. Some of them are actually battery powered. So that means that you cannot simply talk to the product whenever you want to, or some of them aren't powered at all. So it's really, it's a very challenging engineering project to work on. So I want to talk today about those challenges building connected products. And I want to cover basically 3 areas, basically how to make it easy for customers to use it, how to make sure that it actually works, and if it works, that it's performant. And then also I want to touch base on how to make your system scalable. Just touch base, because making something scalable is really, yeah, that would be a subject of like a 3-hour talk or something. All right, so let's get started with how to make stuff easy to use. And the first item I want to cover here is Wi-Fi setup. So imagine you walk into the store, you buy a new shiny product, you come home, you unpack the box, and the product is there. What do you do then? If you buy a speaker, for instance, a speaker doesn't have a display, nor does it have a keyboard. So how can you tell it what Wi-Fi network to connect to and what the password of the Wi-Fi network is? Well, the trick is almost always the same. You do some kind of interaction with the speaker. Either you power it for the first time, or you press a button, or you factory reset it. And then the speaker will start its own Wi-Fi network. Then the phone will disconnect from your home network, connect to the speaker network, send over the SSID and password. The speaker will try to connect to your home network, phone will reconnect, and if everything goes well, your product is set up. Easy, right? Let's now have a look how this works in a real-life scenario. This is the Google Chromecast setup flow. The first thing you should notice is that it's incredibly verbose. There's a lot of screens involved. You literally have to grab the user by their hand and walk them through the process step by step. So the entire setup flow consists out of 12 screens. And after that, there's 8 more screens to basically explain the user how to use the product. And that's only the happy scenarios. There's no bad weather scenario screen there. So let's zoom a bit more in depth. Hey, this is weird. The very first thing that the Chromecasts ask you, you're setting up a Wi-Fi product, and the first thing they ask you is for your location permission. Why on earth do you need that? Well, you need to be able to scan Wi-Fi networks around you to see if there's a Chromecasted setup mode around you. And scanning for Wi-Fi networks allows you to implicitly locate the user, because you can fingerprint networks, so you need to ask location permissions for that. This is something you really have to explain to users, right? Because otherwise they're just gonna think like, oh, here's Google again collecting all of our data. But it's actually not. They really need it for the setup flow. So then you scan for devices around you, you find the Chromecasts. Then we need to actually connect our phone to the network of the Chromecast. So here the phone is gonna disconnect from your home network and connect to the Chromecast network. While that may seem like a simple thing, in practice, network switches actually take easily 10 seconds, 30 seconds, so it's quite a long process, even on a high-end phone. And another important thing here is, you can only do this on Android. Android can automatically swap Wi-Fi networks. iOS cannot do that. On iOS, you need to ask the user, hey user, leave my app, go to settings, change Wi-Fi network, and then come back. So that's, yeah. For a user which isn't tech savvy at all, that's just, they're completely lost. But imagine this works. We then verify that we've connected to the right Chromecast. We give it some setup information like SSID, like the name. And then we can go and select the SSID and enter the Wi-Fi password. Well, here I have a question for you. Who here has like a fairly secure Wi-Fi password at home? Okay, does it include uppercase and lowercase letters? Digits? Random characters? Have you ever tried entering this on like a very small keyboard? It's the worst in the world, right? And it's even worse than that, because there is no feedback loop here. The only way you can get feedback after entering the password is handing over the SSID and password to the Chromecast, have the Chromecast try and connect to your home network, which is gonna be slow, it's not gonna work, so you need to wait for a timeout. Then the Chromecast needs to restart its setup network, you can connect back to it, and then you can figure out what went actually wrong. So it's a very tedious process, it takes a very long time to get feedback. This is where it always goes wrong. I guarantee you that. But there's good news, because you can actually just, in Chromecast, you can basically tell Google like, hey, fetch the password from my device. I think Google is just taking the password from your device backup, or they use a private API, but I'm guessing the device backup case, and they just fill it in for you. That's the good news. The bad news is that we mortals cannot use that. Only Google can. So we always have to ask the user to enter the password. Then we send over the password and SSID to the speaker. We're gonna, ask the speaker to try and connect to our home network. The phone is gonna reconnect to the home network, and if everything goes well, then both of them are connected. You've heard how many ifs I said, right? It's a very, very error-prone process. There's many, many challenges in getting this right, including, but not limited to, some Samsung phones, for instance, they just refuse to connect to a Wi-Fi network without internet. Plain as simple as that. There's an option you can toggle in settings, but yeah, those stuff happens. And the main focus I want to give you here is that there's many bad weather scenarios. This is the flow, how we originally designed it in 2011. And this doesn't even cover all error scenarios. So it's super, super complex, but you must get it right. Because if you don't, a user is completely lost. If they cannot set up your product, they will return the product. And nowadays, you usually get a free 1-star review with that returned product. So, I want to zoom in now how actually an OS update can break your setup flow. So the single most important part of your product can simply be broken by an OS update. So in Android Lollipop, before Lollipop actually, if you would connect to a Wi-Fi network without internet, then Android wouldn't care, and every request you would send, it would just be sent over that network. But starting from Lollipop, they introduced a very neat little trick. If they detected that your Wi-Fi network didn't have any internet, or poor internet connectivity, but you had a full working 4G connection, hey, why don't we route every request over that 4G connection? Sounds like an awesome idea, right? The problem here is that they weren't doing any subnet matching. So even if you would try to ping a local IP, that would be routed over your 4G connection, and hence that would fail. So this completely broke the Wi-Fi setup when Lollipop was launched. Now there is a way to solve that. Hey, you need to do an API check, tell it like only on Lollipop and higher, and then you just say like, yeah, I want to have a network with Wi-Fi capabilities, connectivity manager, give me that network, and then when you get the unavailable call, you can just do your network request, a single request. If you want to like do every request over that network, you can do another trick, and you can just say like a bind process to network, and then every subsequent request you do will be sent over that network. Okay, so if the Wi-Fi setup is so bad and so error-prone, aren't there any alternatives? Yeah, there are. And the single best that I know is what Philips Hue does, and that's just connecting an Ethernet cable to a product. You just ask the user to connect your first product using an Ethernet cable, and from there on, they can just connect as many products as they want, and then our app will handle that for them. This is also what, for instance, Sonos has been doing for the longest time. They now also offer a Wi-Fi setup, by the way. Another alternative would be to use WPS, Wi-Fi Protected Setup. Who knows what Wi-Fi Protected Setup is? That's more people than I thought. Well, this was a very promising technology. You just press a button on your router, you press a button on the product, and if you do that within a particular time window, they would just do a handshake, exchange a password, and everything would be set up for you. Well, in practice, the problem was that, yeah, the button on Wi-Fi routers looked different on every router. And also, remember that most people don't even know they have a router, so people simply couldn't find the button. That, and also, yeah, it had some obvious security issues, which meant that it never really broke through. So what can you do then? You can replace the network switch with another way of sending over the password and SSID. So you can send it over NFC, high-frequency sound, or you can scan a QR code, depending on what the capabilities of your product are. But then people still need to use the Wi-Fi password. Another alternative is, if you're building an Apple-only product, you can introduce an Apple MFI chip, and then you can use their wireless accessory configuration tool, which is baked into iOS, and then they completely handle the setup for you. Users don't have to enter a password at all. But yeah, this only works with Apple devices, so if you want to support both Apple and Android devices, then yeah, this simply doesn't work. So a small pro tip, should you ever want to attempt to build your own wireless Wi-Fi setup, well, give the setup network a random name. Don't call the network setup, because if you're debugging your product in the office and 2 people put the product in setup mode, then you don't know which network you're connected to. Super, super frustrating. Plus, it's also a security risk in the field, obviously. So just append some random characters to their network name. Also, Chromecast does that, and then you're good to go. Okay, next topic that I want to cover is prepare for bad weather scenarios. And here I actually want to zoom into a Hue product. Last year, we've launched the Hue motion sensor. And the motion sensor is actually quite cool because it has dynamic behavior. And what we do is, if you buy the motion sensor, we guide you to a setup flow, which is just 4 simple screens. And then after those 4 screens, we program that dynamic behavior. So if there's sufficient light in your room, we don't turn on your lights. If it's dark, but it's not in the middle of the night, then we turn on functional lighting, so the lighting go on full brightness. If you, however, enter the room in the middle of the night, we turn on your lights dimmed. So it's super cool, right? It's dynamic behavior, and we just give it to you out of the box, 4 screens to click through. So now you're going to say, that's super easy to build. Well, actually, let's see at some cases that could go wrong. In this screen, we're looking for a motion sensor. The people have pulled the battery plug, so the motion sensor starts looking for a network to be joined into, and we also start looking for that sensor. Well, the obvious case here is, what if you don't find a sensor? But there's also less obvious cases. What if you find more than one sensor? That's as tricky as that one, right? Or what if you lose your authentication to the bridge while you're doing it? What if there is no room to add a new sensor in the bridge anymore? And when you select the room you want to use the motion sensor in, what if your bridge doesn't have any rooms? What if some other user deletes a room right when you select it? What if there isn't any room with lights in it? And when we program this dynamic behavior, we need to program a bunch of resources in the bridge. So this generally takes a while. This can easily take like 15, 20 seconds before everything is set up. And yeah, we all know how good the battery life of our mobile devices are. So what if your mobile device reboots in the middle because the battery is dead? What if the bridge receives a firmware update? What if programming one of those things actually fails? What if the bridge is full and it doesn't fit anymore? But you can check for that, right? So we check up front, do we have enough space on the bridge to program this? But what if then there's 2 different users programming the same stuff at the same time, so then the check doesn't hold true anymore? So there's so many places where it can go wrong, and the entire gist of this is it's almost impossible to reproduce manually. You can try, but you're never gonna stay sane while doing that. So that's why I advise you to build a simulator. And now you're all gonna be like, yeah, but we're not Philips Hue, we don't have the resources to build a simulator. That must be a very tricky thing to build, right? Well, actually, it's not at all. You can just use a simple strategy pattern, which you're probably gonna need anyways, because remember, you can either communicate locally to your product or remotely over your own servers. So you already have some kind of abstraction on top of that. Why not also build a simulator strategy? A very simple class implements the same interface, and you can then simply hard-code responses. You can simulate bad weather scenarios. Or, my personal favorite, you can simulate dynamic behavior, which is super cool, because then every time you would ask the strategy, like, hey, what's the color of my lights? You just always return a different color. So then you can actually see all of the gradients in your app, how they change based on what color the light has. And then you can easily like test your animations and so on. It makes it a lot easier to debug a lot of scenarios. I also have a pro tip for this section, and that is try not to use the word device. What is a device? Everything here can be a device, right? So just name it, it's a product or an appliance or name it by what it is. This is a speaker, this is a bridge, this is a phone. Otherwise, you're going to have these confusing conversations with your coworkers. Okay, so far for keeping stuff easy to use. Let's now make sure that it actually works. And the first thing I want to talk about is discovery. So there's two kinds of discoveries, because you can either be locally connected to your product or remotely. So when you start up the app, you need to search for all of the products you can connect to. Well, the local discovery always works multicast based. So your phone just broadcasts a message, hey, here I am, I'm looking for speakers on the network. And then the speaker can either directly respond to the phone, or it can also just broadcast, hey, I'm a speaker, is there anyone who wants to connect to me? So typical protocol implementations are SSDP or MDNS, but there's alternatives. You can just take the subnet and then try and reach every possible IP address on the subnet. That's an IP scan. Works effectively, but it's super, super resource heavy. The other thing you can do is ask the user to enter an IP address. Probably the fastest discovery, but yeah, the least user-friendly. And then the last thing is to have some kind of proprietary IP server. I'll explain that in a second. At Philips Hue, we actually adopt all 4 of those, because it's so critical that user can actually find their bridge. So what is this IP server about? Well, actually, you can go on any network to that URL, and then we will return you what are all of the bridges connected to that network. So at regular points in time, our bridges check into our backend server, and when they do, we basically register their external IP, and then also their internal IP and the MAC address. So nothing user identifiable, nothing like that at all. And you can just go to that URL, you'll get a JSON array, and then you just know at what IP addresses bridges could potentially be. You just try those out, and then you start authentication flow. The reason why we have this, by the way, is because this is the only mechanism, besides entering the IP manually, that works in a web app. So then we also have remote discovery. Remote discovery is fairly simple. You just connect to your remote backend, and you ask your backend, hey backend, which are the products I am allowed to communicate with? It will never return you all of the products, because yeah, in theory, all of your products should be connected to your backend, but yeah, not every user is allowed to connect every product, so there's an extra level of authentication on top. One side note, in order to do this, you need to have gone through the local setup first. So let's now have a look at a real-life use case where we're going to optimize the discovery. We're going to build a simple app. The app doesn't know when it gets opened, so a user could open it when he's at home or at work. We have no idea. And what we need to solve is we need to look for all of the devices the users can connect to. And interesting here is that the bar for mobile apps has been set incredibly high. Users' expectations are sky high. And users don't appreciate the complexity of your app. They've bought a high-end phone, so they expect your app to respond fast. So let's see how we can actually make our app fast. Well, the most basic thing we can do is we open up the app, we start a local discovery and a remote discovery. We can do both in parallel. The local discovery is going to finish, then the remote discovery is going to finish, and then we're going to poll every device to get its latest state. Because only if we know whether a speaker is on or off, we can allow the user to start controlling it. Let's see how that looks. So the app starts, we open up the app, local discovery finishes, remote discovery finishes. We've polled the local devices, we've polled the remote devices, and now you can start controlling all of those products. Looks okay-ish, but it's slow. It takes 5 to 10 seconds, and if you don't find any device, yeah, then the user will look at the blank screen. So obviously we can do better there, right? The obvious thing is to use a database. Well, what we're going to do is, whenever we start the app, we're just going to get the products from the database that we already know, so we can immediately show them to the user. But the trick here is we can do that, but then we still need to start a local discovery and remote discovery. We still need to poll the devices locally for the state and remotely for the state. So while this may look a bit nicer to a user, it's still exactly as slow as the previous scenario. One side note here is, if you build this, you need to also offer the users a way to delete devices from their list, because you can go and visit a friend, connect to his speaker, and then when you're at home, you don't always want to look at his speaker, which you can no longer control. Okay, so how can we make this better? Well, instead of just remembering the device, we can also remember their previous state. Well, this is interesting. You could say that if I leave my house in the morning and I turn off my lights, and I then come back in the evening, the light should still be turned off, right? So that's a fair assumption to make. So let's make that assumption. You can already see, we're gonna assume that the kitchen speaker is on, the bathroom speaker is off, and that the work speaker is on. And when we start the app, we're gonna do the discovery to basically know what their address is to communicate with, and then we're gonna fetch their state. So we open up the app, the user immediately sees something pleasant, we've discovered them locally, discovered remotely, so then we enabled the UI when we discovered them, but then suddenly we discovered that the kitchen speaker was actually in a different state. Let's look at that again. So we were assuming the kitchen speaker would be on. We now have the address of the kitchen speaker so we can connect to it, and then we suddenly discover like, oh no, the kitchen speaker is off. Well, while this may look a bit weird, it's actually not weird at all, because in practice you can always have multi-user scenarios, 2 phones talking to the same product, and that would look exactly the same as this looks. One important side note to make here is, you can't always make this assumption, saying like, I'm gonna assume my product is in the lost state. And the reason for that is like, think about, for instance, a security use case. You're building a connected door lock. Well, do you really want to show the user for like a blink that their phone was unlocked while it was actually locked? That's just gonna panic the user, right? So depending on your use case, this may or not be a valid assumption. Let's do it even better. Instead of just remembering the devices and their state, we can also remember their latest connection info. So if we just, for every product, remember which was the last Wi-Fi network we've seen the product on, and which was the IP address on that network. IP addresses usually don't change that much. Then we can just open up the app and immediately allow the user to control it. We still need to start local and remote discovery, because people could have, so the IP address could have actually changed, or they could have moved their product from their work to their home location, and so on. But it makes stuff blazingly fast. You just open up the app and boom, everything is ready to go. We could still be mistaken about the state with the kitchen speaker, but this is like the nicest thing you can actually do for a user. A pro tip here, when you're building a connected product, we as engineers, we typically tend to like think about all of the scenarios and then take all of them into account. Like you could say like, yeah, our app should be able to seamlessly swap from a local connection to a remote connection. Well, that's not true. You can simplify it and you can just always push the connection through a disconnected state. And then the disconnected state is the state where you clean up all of the subscriptions, all of the resources. This just reduces the test vectors of your app. Simple way to make things easier. All right, let's now maximize the control speed. To make your product work fast, you can basically do 4 things. First, always prefer a local connection, because a local connection will always, by definition, have fewer hops and will always be slower. No, always be faster. Sorry about that. Secondly, a local connection also doesn't have any cost involved. A connection over your backend, every server request you do has some kind of cost attached to it. Local connections are faster and they're free, so always try to use those. But when you're using the local connection, you need to optimize the hell out of it so you're making the most efficient use. You also need to reduce the amount of requests you make. And then also on the UI level, you can do some nice tricks to make stuff appear faster. Now, one side note here is that why am I stressing so much about optimizing the local connection? Well, that's because remote connections typically aren't that critical. Do you really care if you're out of house, that if you turn off your lights, that they go off after 50 milliseconds or 2 seconds? That doesn't really matter that much, right? At least if you're starting up, it doesn't matter. Even for us, Philips Hue, that's a super important KPI, because we do cloud-to-cloud integrations, and therefore also our cloud speeds must be as low as we possibly can get them. So that assumption stopped working like a year and a half ago. So, preferring the local connection, how can you do that? Again, let's go back to our strategy pattern, add a composite pattern on top. We define a composite strategy, and that basically will just try every strategy in a predefined order. So if you then do a request to your speaker, you're just gonna see like, hey, simulator strategy, are you available? No, because you're a release app, not a debug app. Okay, fine. Hey, local connection, are you available? Yeah, I'm available. Okay, let's send a request over there, and otherwise we would send it over the remote connection, and you can even extend this and say like, yeah, if there is no connection at all, I want to log this information. So then you can make like a logging strategy. To optimize a local connection, I'm not gonna really cover this in depth. You just need to make sure that you use all of the latest technology, that you set the right caching headers, that you have the right compression and so on. The TLDR of this is use a modern state-of-the-art library, like OKHTTP. A small tip that I want to give here is, so sometimes you may notice that your device isn't really behaving as fast as you would expect it to, so then you need to dig a bit deeper, like checking if your sockets are actually being reused, or that you don't have any interference between TCP and UDP traffic. Well, you can actually use a tool for that called Wireshark. Who here knows what Wireshark is? Whoa, that's a lot. So then you probably also all know that if I connect a laptop to this network, like in this setup, I cannot see the communication between the speaker and the phone, because that's point-to-point, and yeah, basically your network card will ignore all of those packets on the Wi-Fi network. So if you want to sniff that communication, you need to add a hub in between, which will basically forward its input to all of its outputs, and then suddenly the computer will receive everything. Now, reducing the amount of requests. There's basically two use cases for this. Toggle sequences. If a user says like, my light should go on, off, 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 you don't want to send all of those requests, right? If you just send the latest off, that's fine. And the other use case is if the user does multiple things to the same endpoint, like, hey, turn my lights on to brightness 30% and then to color blue, you don't want to send 3 requests for that. Wouldn't it be nice if you can combine them? Well, it's actually super easy to build. And we're gonna use a state-of-the-art technology called a hash map. What you can do is, which is a very simple trick, because most products use a REST endpoint anyways with the JSON communication protocol, why don't we put all of the JSON attributes and values in a hash map? So every time when you say, hey, turn my lights on, I just put the on attribute with the right value in the hash map. And the hash map will only contain one value for each attribute at any given point in time. And then what we also need to do, obviously, is when we set some value, we need to request for an update to be sent to the product. So then you do a send update. What the send update does is, it does nothing more than just ask your strategy to do a request. And we always pass in the same update request object. So far, so good? Now, the update request object is super simple, a custom-made class. It's basically a member. It's final, but it didn't fit on the slide. And what this is going to do is, it provides you the endpoint, and it also has one simple method, get the attributes. And in get attributes, it's basically going to sample the hash map. It's going to take all of those values that are in there at a given point in time, and then clear the hash map in a thread-safe way. What the strategy will then do is, the strategy has a queue. And the queue can now be super simple. The queue can just be a set, a collection which can only contain every object once. And if it is a set, then the doRequest method will just, add the object to the set. If it's already there, then fine, it won't be added again. And if it's not there, then it will be added. And then it will just trigger its logic. So this is a very simple mechanism which basically allows you to sample all of the attributes that are pending, send them over in one bulk, and then see if there's new attributes to be sent, or if you can just stop and wait and be idle. By the way, this is actually in actual products that has actually been shipped. Okay, so then also on the UI level, we can do some interesting stuff. Compare the right and the left app. If you look at the left app, what happens there is I press a button, And then I'm actually going to communicate to the speaker. I'm going to wait for its state to change, and only when that has changed, I'm going to update my UI. Whereas on the right-hand side, we don't care. You just press the button, we're going to assume that everything is going to be successful, and we're going to instantly show it in the UI. Which of these do you prefer? The right one, right? And actually, the rightmost app was almost a second slower in controlling the speaker. But they really cover it nicely. They also do this nice animation where they rotate from pause to play. So if you properly give assistance to the user, you animate it a bit, you assume that your product is going to work successfully, that's going to significantly improve the user experience. And then the final pro tip here is always measure, never ever assume. I'm too ashamed to tell you how many times I've said to like one of the testers, what? 1,000 requests per second? That cannot happen. My app doesn't do that. I know how the architecture is. And that we then put a proxy in between and you just see like that it's even worse than that. It has happened countless times. So always measure that. So we've already arrived at the last part, how to make stuff scalable. Well, let's start building a connected system. We have a team of 4 engineers. And every engineer, every sprint can build exactly one feature. So the first sprint that we start, we're going to build 3 features. We don't want to overload the team, right? But the next sprint, we can again do 3 features, but we have some maintenance to do, like a very small amount, like only 10% of maintenance on all of the old features. But if you scale that, then the third sprint, you need to do the maintenance of the features in the first sprint and the second sprint. So it's cumulative maintenance. So after 4 sprints, suddenly, boom, you have to drop a feature. And if you scale that up, then after 8 sprints, again, you lose a feature. And you already know where that's going to end up, right? The true cost of software is in its maintenance. So we need to make sure to optimize for that maintenance. So how can you do that? Focus on automated testing. I cannot emphasize that enough. And automated testing is on multiple levels. You need to have a very extensive unit testing safety net in place. Something that runs blazingly fast, that you can just trigger and get instant feedback to know like whether all of the blocks in your app are still working the way you intended them to work. That doesn't mean, though, that they're going to work nicely together. So to do that, you need to have component tests. So integration tests for the component. And what I usually do is I just take the app, I cut off the UI layer, I cut off the network layer, and I test everything in between. And that has the benefit that you're testing integrations, how everything works together, but you're cutting off all of the flakiness. Because tests need to be reliable. If they're flaky, you're going to go insane. But then finally, you also need to have end-to-end tests for your entire system. I press a button in the app, and I test that the light actually goes on the lamp. That's also something that you need, and the reason for that is because if you grow your system, you're going to have such a vast amount of use cases that you need to automate those, because otherwise you simply cannot do the regression tests every release anymore. So you need to have that automated. Now, hopefully I don't need to tell you that you really need to have a good architecture, and hopefully I also don't need to tell you that a good architecture isn't something that's designed by somebody who read a design patterns book. A good architecture is something that is super simple. You open up your code base, you go there, and you're like, yeah, of course it's like this. You don't need to add all of those placeholder interfaces on top and blah, blah, blah. That's all not needed because we have a statically typed language, whether it's Java or Kotlin, and we have amazing tools, an amazing IDE. So if you later want to add an interface, fine. Have IntelliJ do it for you. You don't need to put all of those stuff in place from the get-go, right? Except if you're building a library with a public API, that's a different story. But for your own product, you simply don't need that. And then over-engineering has a huge cost attached to it. I think that's clear. And then hype-driven development. This is an interesting one, because what we always want to do is we want to stay on top of our game. We want to yeah, make sure we use the latest technologies because they could potentially benefit us. But on the other hand, should we choose the wrong technology, then yeah, we're scaling our system, we're only adding new features, we're scaling stuff on top, so then you're suddenly gonna have a lot of legacy code you'll have to continue dealing with a framework that never really became mainstream. So it's like, the art is finding the right balance between being conservative enough, but also being innovative enough. And then, as a final remark, may seem like an obvious one, but you really need to think before adding new features. In all honesty, at Philips Hue, we've made quite a few mistakes in this area before, so that we decided to build a particular feature which we thought was going to be useful for a lot of people, but in the end, it turned out to be a very complex feature with a lot of regression on it, and then only few people were using it. And then it's just a waste, right? Because you're not serving the majority of your users. And giving users a feature is easy, but taking it away, that's a different story. So think well before adding new features. Now, my failure Hall of Fame, pardon me, this is mostly Android related, but it's simple things. I'm going to quickly go over it. Like, I once thought it was super easy to detect whether you're on a Wi-Fi network without internet. Well, turns out that's just impractical because you run into a system timeout on Android, a DNS timeout, which you cannot set, and that just makes it too difficult to detect this. Impractical, actually. Don't run tests on an Android device. Always run them in a JVM. They run a lot faster. You don't have this nonsense on the CI that your emulator disconnects and so on. So it's just better to stay sane. Take multiple orientations into account, so portrait landscape mode from day one, because if you have to add it later on, it's going to be a mess. And the key thing to remember here is you're going to need to add it at some point, because you're probably going to start with phones, but once you add tablets, there is no standard orientation for tablets. So then you need to have both orientations. So it's just a matter of time for any app when you will get this. Don't nest fragments. I'm personally not against fragments. I actually like them. But if you start nesting them, then yeah, it has gotten a bit better, but it's not good for your sanity, let's say that. And then this is also an interesting one. On Android, you have an eventing mechanism called broadcasts. So you send up something here, and then magically something receives it, which is awesome, right? It's loose coupling. It's really not. Because that is completely, it breaks your click-through debugging. So then you send an event here, but you cannot step with your debugger to the receiver. That becomes super cumbersome. And then also, it's very hard to have the proper tests in place to make sure that the receiver is still subscribed and is subscribed at the right point in time. It's very better to define clear contracts and then stick with those. Also, threading-wise, I've seen a lot of apps make the mistake of just like not really being aware of what thread they're on, so then they just like post a runnable on the UI thread or on a background thread just to be safe, right? Well, you really shouldn't do that because that's such an amount of code pollution. What you should do is you simply say like, okay, here's my architecture, I'm gonna draw the line here. Everything below is gonna happen on a background thread, everything on top of a UI thread. You make the decision once, and then suddenly this becomes a non-issue. And then last but not least, null checks, or in general, checking for cases that shouldn't occur. So you have two different approaches. You can either do defensive programming or you can do offensive programming. My point on this is do offensive. If your app isn't prepared or your application isn't prepared to handle a particular scenario, there is no way to recover from that, right? You can make it fail silently, but is it really good for users? It's better just to be aggressive in it. If something shouldn't be null, fine, it shouldn't be null, and just have it crash there. You're then going to find that crash either during development, your QA cycle, or the beta testing. You're going to find it before you go to production anyways, but when you find it, you can actually solve the root cause of the issue. I've actually written a few blog posts about this. One is how to write awesome unit tests, which you all want to do. And also one is advocating exactly this case of why your app should crash. So let's wrap things up. So I hope it's clear now that in software design, the consequences of your decisions are only gonna become apparent for years. And I can say from my personal experience that I've usually hoped that, yeah, I would only notice my bad decisions after like half a year, but in reality, it ended up being like already after 2 months or maybe even a few weeks. So we have to deal with them anyways. You really need to do things right. And then as a conclusion, so developing connected products is hard, but developing connected systems is even harder. Make sure you get the most of your local connections, keep things simple for the user, focus on automated testing, and have a proper architecture in place. Then finally, I want to give credits to the images. I didn't take them myself, but interesting side note, all of the products that I showed here are products that I've actually worked on and which are connected products. So that was it. I want to thank you very much for coming to my talk. Again, I'm very active on Twitter @Molsjeroen, and I also actively write a blog, so should you be interested, feel free to check it out. Thank you very much. I think we have some time for questions, if there are some. Okay, fine. Thank you, and have a great weekend.
Hi, everybody. How's it going? Happy Friday. Have you had a good week? Yeah? You feel excited. Lots of excitement. It's been fun. Yeah, it's been a great week, and I'm glad to help you in one of the last few sessions to tell you a fun story. So today, we're going to do a talk that's a part of a series called the Zero to App Talks. And in this talk, we're going to build an application. We're going to build a universal translator with Firebase. And this is a talk I love to do on the road because I'm a monolingual person. I only speak American English, which can be challenging at times. But this can make it easier. But before I get into that, let me tell you a little bit about myself. Hi, I'm Jen. I am a developer advocate at Google, focusing on cloud platform. And I spend a lot of time playing with Firebase stuff as well. And in this role, what I do is I come and I get to tell you, all of you, great stories about stuff involving Google Cloud and Firebase products. And I also get to go back home with stories that I hear from all of you about what we're doing great, what we could be doing better, what you're interested in, to help us figure out what we should be working on to improve our platforms. So I always love hearing from all of you, whether it's a story about something awesome you created, or a challenge you're facing with a Google platform or API. So please do reach out to me if I can ever help. You can find me on Twitter. It's a pretty easy place to find me. Just drop me a DM. I'm miming codes. And if you'd like to, I don't have my website URL up there, but if you'd like to ping me via other channels, I'm also miming.com. You can find other ways of contacting me there. So we're going to be doing some code. But before code, let's do story time. Who here likes science fiction? A few hands went, okay, everybody's hands went up. Yeah, I figure that might be, some selection bias with that. I love sci-fi too. And it's actually been a big influence on me growing up. I watched a lot of science fiction, and it's one of the things that helped guide me towards engineering. I got to see all the cool stuff people were able to accomplish with technology. And one of my favorite science fiction series growing up was Star Trek. And Star Trek was really cool, partially because they had lots of really cool technology that allowed them to accomplish tasks, or I suppose to make the writing easier. For example, one of these technologies was this magic handheld device that would allow them to talk to anyone far away, which seemed really impressive. And it's kind of neat because we already have those today. Another technology that they had was they could just ask a computer. They could just, with words, talk to a computer, and then tea would appear. And that was really cool. And we've gotten part of the way towards that. Like, you can talk to computers, but tea does not always appear, unless you count it arriving by, rideshare eats or something like that. But one of my favorite technologies of Star Trek was the universal translator, which I think was just there as a plot device to make it easier to write and make it easier for us to relate to aliens. But it was still really cool, because no matter what planet they landed on, and no matter who they were talking to, even if they had never had any contact with the species on another planet, after a couple words, they were already completely understanding each other with fully functional two-way communication. And that seemed like such an amazing thing, seemed so cool. And this is the kind of thing that I would love to have, because part of my job does involve traveling around the world and coming to developer events like this, and meeting other people in other contexts that are using our stuff. And I would love to have something to make it easier for me to communicate with them in their chosen tongue. So I decided to solve this problem in the way I solve all of my problems in my life, with code, specifically writing a mobile application. So that's exactly what we're going to do today. I'm going to guide you through the creation of the app to solve the kind of like universal translation problem. And you can kind of see you can kind of see the app, what our vision for it is. It's an app, you select your preferred language to both communicate out in and also to receive language in. So you choose your chosen language for that. You hit a record button, which is either big or small, depending on the platform of your choice, and you will speak into it, and what it will do is it will translate it to many different languages simultaneously, and then anyone else with a copy of the same app will hear it translated to the language that they selected. So that is the app I envisioned to solve this problem. And I'm going to solve it using Firebase, because Firebase is a great way to prototype mobile and web applications. So we'll spend a couple minutes talking about Firebase and the components we're going to use to build this application. So let's talk a little bit about like traditional mobile application development. If I wanted to write this app like a few years ago, the first thing I would probably do is start sketching out the app like I just described, and then trying to pick some back-end components to solve my problems. I'd pick relational databases, I'd pick some cache infrastructure, I'd figure out how I'm going to be sharding my data potentially, or sharding at the database layer. I'd probably have some third-party APIs I'm going to use, and I'd broker them through some VMs or processes running on those servers. And this is a great approach. It definitely gives me a lot of flexibility on how to scale and how to solve all the problems my app will solve efficiently. But it can take some time to get started. But there's other options because we're kind of in the future now. We have lots of different options for solving these problems. And Firebase gives us some interesting approaches to this. What Firebase does is it's kind of like a big bag of goodies that takes a lot of kind of the common tasks of mobile and web application development and gives you really good pre-built backends to solve some problems and a whole bunch of stuff in client libraries that take care of the heavy lifting of communicating with those backends. For example, storing state and storing blobs, which are two of the features we're going to be using. But there's a whole bunch of other goodies in the goodie bag, everything from like static file hosting to, what else do I have on this slide? Remote configuration pushing, authentication, all sorts of other goodies, which are not always fun to keep re-implementing over and over again. And you might just want to use just one of these for an application, and in which case it will work great. But they also connect really well, and I guess the word is synergize. I never thought I would use that in a presentation. They have a lot of synergy with each other, so they're even more useful when you use more than one together. For this application, we're going to use 3 specific things from that goodie bag. We're going to use cloud storage for Firebase, which is a tool for storing big blobs of data. Particularly, we're going to use this. Specifically, we're going to use this to store the recorded audio of the user speaking into the app so that we can work with it in the cloud. We're going to use authentication, partially so we can just identify the users to our application so that they have access to their specific data, and also so I can prevent anyone on the live stream from jumping in on my app in real time, because that would not be very fun. Or it might be fun, but not for me. And we're going to use my favorite goodie from the Firebase goodie bag, which is the real-time database, which is actually the first goodie from the Firebase platform. It was one of the original products. And it is a backend that is built around transferring real-time data. So let's dig into a few of these in a little more detail. So cloud storage for Firebase. So dealing with cloud storage and just general blob stores from a mobile app can be a little bit tricky at times because you have to figure out how you're going to handle the key brokering and how you're going to, for example, set limits on individual users uploading certain amounts of binary data. Getting all that access control can be kind of tricky. So what Cloud Storage for Firebase does is it gives you a nice default configuration so that you can just call the client library, store your binary data. It does a good thing by default. It'll send it up to a cloud storage bucket, which will then make it globally available for any other client anywhere around, being served up through all the different points of presence that cloud storage provides. And it also has all the client library components for automatically syncing to clients that care about it. So you don't have to spend as much time moving around those bits and stuff like that. So it's a problem that is deceptively complicated, and it makes it a little bit easier. Authentication is another very important thing, especially if you want to restrict access to an application or you have data that is user-specific, for example, like user profiles, where you only want users to be able to edit their own profiles. Security is important. And Firebase authentication is the kind of first step in building out that security framework for your apps, because you have to be able to identify users before you can figure out what they will have access to. And the way Firebase authentication works is it gives you pre-rolled implementations for a bunch of different authentication schemes. For example, we have pre-rolled backends for OAuth, like social login providers like Facebook, GitHub, Twitter, and Google. Has anyone ever rolled their own multi-platform authentication provider with OAuth? A few people. Was it fun? No. Oh, someone said that's the first time anybody's ever nodded. I think authentication is pretty cool too, but I did not enjoy building both a Twitter and Google authentication broker at one point. They use different interpretations of OAuth. But anyway, we've already done this with the Firebase authentication stuff. And we also have like username and or email and password authentication for users that don't want to do a social login. We added phone number authentication a few months ago, which is pretty cool. And there's client libraries for integrating with existing authentication systems. You can mint the JWT tokens to integrate with your SSO or any existing authentication system, which works pretty well. And one of the neat things about Firebase authentication is each one of these login providers boils down to a unique identifier for that user across all Firebase services. And you can, if a user comes in via a different authentication flow in the future, you can, give them access to the same data because they're still identified as the same user to Firebase. And then finally, my favorite part, the real-time database. So the way the real-time database works is it's kind of like a big old ball of JSON in the sky. Because we all love JSON, right? Mostly nods, a few shaking heads. I guess it's an opinionated crowd about data storage formats. But I like JSON. It's convenient. It's pretty easily human readable. And so the way it works is you imagine all of your backend data as one big old ball of JSON. Your applications can write to certain nodes or subtrees. Anything you could put in JSON, so like booleans, strings, numbers, stuff like that. And then your clients will tell the real-time database what subtrees or what queries against subtrees they are interested in. And then the client libraries will work with the server to make sure that any client will always get push updates for the parts of that big old JSON tree that they care about. So we'll handle all of the synchronization, all of the background threads for the network transport, cache invalidation, which is never fun to work on yourself. We give you good sensible defaults for all that stuff. We also have APIs for handling both short duration offline, like driving through a tunnel, as well as long duration offline, like going for a mega hike across Appalachia or something like that. So you can configure like pinning and all that stuff for handling those offline cases too, which is also not very fun to roll your own. So enough talk about the Firebase stuff. Let's show it to you in action. Let's do some code. Sound good? Yay! Yes. OK. So let me show you someone was especially vocal. I like code. So this is the starting application we have up here. Let me make it bigger so it's even bigger on the big screen. See if I can get Visor to cooperate. There it goes. That's pretty big. And it doesn't really do much right now. So it's just kind of a shell of an Android app, which of course means it's quite a bit of code because it's an Android app. And Android apps often have lots of code inside. But you can see the controls I described earlier where we have a spinner, a drop-down box for picking the language we want to speak and understand. We have a record button for recording an audio clip, and then any translated text to the global chat room essentially will be put here. So what we've already done ahead of time is I've already written the code that does like the recording, like taking the bits out of the media recorder and bringing them down to a local file on the Android device and all that kind of stuff. I've also gone ahead and set up all the Gradle dependencies for Firebase because that's not terribly fun to watch and sometimes it can take a while to download. So when you're going to get started by adding Firebase, actually taking a step back, this is a kind of a general flow I'll use for building applications if I'm going to be using Firebase, is I'll kind of wireframe out just the front end. I'll get the front end, I'll get it looking the way I want, and then I kind of get it working locally, like without much real behavior, and then I kind of add Firebase into it to wire the UI components directly into the real-time database, and then before I know it, the app's just kind of already working, which is pretty cool. So if I'm going to be doing that, if I'm going to be starting from this like UI wireframe, the first thing I'm going to be doing is pasting in some code that will go and get an instance of the different Firebase components I'm going to use. So I'm going to be using storage for the binary files. I'm going to be using authentication for doing all the authentication handling, and of course the real-time database for moving all of that fancy fun state around. Then I need to be able to handle, the first thing I want to do is I want to write all the data to the different Firebase services I'm going to use. So I'm going to be uploading a file to Firebase. So what I'm going to be doing here is I'm going to be using the references that I've initialized in the onCreate, and I'm going to come down to this upload file method, which gets called when the button gets pressed and the recording finishes, and I'm going to set up the references. So what I'm doing here is I'm getting a couple different references. First, I'm asking that storage instance for a reference, kind of a handle on a directory, to a directory in cloud storage called uploads. So just give me a handle on the uploads folder, and this is going to establish the sessions and get everything ready to start moving data back and forth. And I'm also going to ask for a reference to the real-time database. And what I'm going to do here is you can give it a path to any subtree within that database. I'm just going to refer to the root uploads node. And then I'm going to call push. And what push does is it gives you a monotonically increasing, globally unique identifier. It gives you a database ID. And this one is appending it to that path so that everything I write will write to that location. And what this allows me to do is have many clients that are writing at once and have all the stuff go in serially. And the client library will take care of correcting for clock skew and all that other not fun stuff. So with those database references in hand, I'm going to upload the file to storage. I'm going to take, and I'm going to upload it. I'm going to name it. Well, first, OK, so I'm getting an upload ref, and I'm naming it based on that monotonically increasing identifier that I got from the real-time database. I'm also going to configure some metadata on that file. Then I'm actually going to push the bits up to the cloud. I'm going to get that recording from the local file system. I'm going to associate that metadata that I defined, saying the content type and that kind of stuff, so that I know how to transcode it later. And the first thing I'm going to do is add a handler that will respond to failures. So if for some reason I am unable to upload, this method will get called. So this could be because of something that happened on the network, could be because of an authentication failure. Anything that caused it to fail will trigger this, and it passes in an error object that I'm not actually using. I'm just toasting a message that says I'm sad. Then I can add another handler, and what this handler is going to do is it's going to respond to a successful case. So in the case that I'm successful in uploading the binary of the recording, then I'm going to create an object, just a POJO, which I should probably convert this to one of those wonderful Kotlin data classes, but I haven't yet. So I'm going to create a recording object that's just a POJO that I'm going to put a bunch of the metadata about that recording into. Then I'm going to take that and I'm going to write that POJO to the real-time database. So it's going to get sent up there, and it's just going to get broken down into an associative array of stuff in the real-time database. And I can use that for downstream signaling. So let's go ahead and run this application and see what it looks like. Boop. So we're going to run it on my Pixel. And let me bring up the database viewer for the real-time database, and let's see what happens when we try and use this application. So the Gradle build is running, so we'll do the dance while that happens. So when I fight with my coworkers and foam swords, like that comic Once Upon a Time said. And now we're installing the APK. This will happen a few times during this talk. OK, so our application is running now. So when we hit record, it should be able to upload something to the storage, and then it should be able to, we should see it appear in the real-time database if that's successful. And my app crashed. It says it keeps stopping. Oh, I think I forgot to log out after I rehearsed. So let's go see why it crashed. And it says illegal state exception on the recorder. Uh-oh. I think Android forgot about some permissions I had set ahead of time. So I'm going to take just a moment troubleshooting this before I go in and move on to the next step. And then we'll fix this after the fact. So this is under, so it's asking for an application. We app permission, because I was lazy and didn't actually add the code that does the permissions the way you would expect. So it's up there, and it has the permissions for recording. So why are you grumpy, app? You were fine this morning. Let's give it one more kick. OK, so we're gonna pretend that worked, and we're going to keep on moving. Because the thing that would happen if it was cooperating is it would pop up the message that said it's sad. So if we go back down here, it would say, where did that method go? So we're below on create. We're down here in the upload file method. So what I hadn't done ahead of time is my backend was already configured to use Firebase authentication. I was requiring clients to be authenticated as a user to be able to upload data to storage, as well as to be able to write stuff to the real-time database. So because those were set up on the back end and I hadn't actually authenticated on the front end, it blew up in a little fireball and should have just toasted and said, I failed to upload the audio. So the next step for that is to go up ahead and add authentication handlers to our app. So we're going to go up and we're going to add that, and we'll see if this fixes my application, which I don't think it will, but we'll find out. So we're going to go back up onto the onCreate method on our Android app, and we're going to set up authentication. And the way Firebase authentication works is just the regular Firebase authentication libraries provide kind of low-level handlers for doing like all of the different passing of chunks of data around and keys and all that stuff to do the authentication. But they don't have a strong opinion about what the UI flow should be. So you'd have to kind of like, which makes it great for integrating into a UI flow you already have or styling it like the app the way you want to style it. But that's not always the case, especially if you're just hacking out an app quickly. So in addition to that, we have something called Firebase UI, which is a set of kind of default implementations for the UI flows for a bunch of different Firebase things. And I use this a lot for the authentication stuff. So the way they work is they will, for Android apps, they will, if you are not authenticated, you can start an activity that will handle the authentication flow for you. So what you do is you use the authentication handler to determine if the user is currently authenticated. And if the user is not authenticated, it's going to be equal to null. Also old-timey. And if the user is authenticated, then we can have our app behave as it would. In this case, we can have it listen for translations. But if the user is not authenticated, we want to authenticate them first. So we're going to put in a code snippet that takes care of that for us. So what this code snippet does is, it's a wide snippet. Anyway, so what it does is it goes and it calls a method on Firebase UI to start an activity for result. And then it will create the activity, or rather create the intent to create the activity that does the authentication flow for us. And what you do here is you set the different providers that you want to support. So in our application, I want to support email and password login and Google login. But I could put other ones there for Facebook or for my own SSO provider, that kind of stuff. So let's see if it just magically starts working again when I hit the run button. Otherwise, I'm going to go to the other app, which I've pre-prepared on another package name just in case this kind of thing might happen. Funny how that happens, isn't it? Hey, at least it starts. Hey, it actually started. I can at least show you the authentication flow. So I was not authenticated with this application, so it immediately took me over to the login flow. And this is the default thing. I can actually put some other metadata on the authentication flow to give the user some hints on the screen, but I didn't bother doing that. So we can authenticate. I can authenticate as my user, mimingcodes@gmail.com, and it's going to take me back to the application. And then we will see if it lets me record now. If it's magically started working. Nope, it stopped working already. Hopefully the other one works. Anyway, so now I'm authenticated, so I should theoretically be able to write objects to the real-time database and to storage. So let's actually see that in action on the other prepared application. So, and this one's still recording. Oh, because the microphone. Someone just told me that I had another application that had been recording for hours, apparently, which locked out that resource and then triggered a case that I did not anticipate in my application. Because mobile development can be hard sometimes. Let's see if that fixes it. Hello, world. So it won't actually translate anything yet, but we see that it was successfully uploaded. And we see that it appeared here. And this is the metadata about the file I uploaded. And if we go over to storage, we can see that there's an uploads folder with a bunch of files in it because I forgot to clear them out. But you can see that there's one from right about now. It's about 4.7 kilobytes of me saying hello world. But our application has not actually responded to it. So I've sent data up to the cloud so I can do stuff up there. But my application's not reacting to events in the cloud yet. I'm only writing data. I'm not reading it. So let's implement that part next. So what we're going to do is we're going to go down to this listen for translations method, which is the method I call when like my application is set up and it's ready to start receiving data from Firebase. So listen for translations. what we're going to do here is grab another snippet of code, and we're going to do something we do a lot when we're using the real-time database. We're going to get another reference to a location on Firebase. This time, we're going to listen to the path translations, which is where all the translations are going to end up. And in the next snippet, what we're doing is we are adding an event listener. Let me see if I can make this a little wider. Fighting visor here. It does not want to today. It is a silly thing. Anyway, okay, so here it is. You can actually see all the code. So what this one is doing is we're doing a query against that tree. Specifically, we don't care about the stuff that was uploaded an hour ago or a day ago, because it's all going to be up there. We only care about the stuff that people are currently doing. So we're going to add a query, a very simple query, to the limit to the most recent one object that's been uploaded to translations, or it's been written to translations. So what this will do is when we first connect, we'll get the one most recent one. And then as people continue to use the application, we're going to continue to get callbacks called whenever another one of those things appears. Every time one appears, it's going to send us one down. And it is a child event listener, which means that we're going to give the path just above where we want. And it's going to give us, whenever a new child is written up there, we're going to get callbacks for a variety of events. So there's a bunch of events that I didn't bother implementing, but in production I actually would. Like for cases when the children get deleted, what should I do? Should I display an X on the screen? If the child is changed, but we're just doing the child added. So we're only handling the case where a new one is written. And what we're going to do is, in this method, which just gets called whenever a new object appears, the first thing we're going to do is take the snapshot. The snapshot comes in whenever you get a kind of a read event from the real-time database. And it's an immutable snapshot of the data at the time the callback is called, at the time the event occurred, essentially. So if things change while your callback is running, it's still going to stay the same, because otherwise that would be crazy. And it has a bunch of metadata in there. One of the pieces of metadata is the key, which is going to be the same key that we defined way above on that push method as to propagated through the system. And then once we have that key, we're going to listen for the language that we have picked on the spinner. So let's go down into here and let's implement that. So what this one's doing is it's null checking the translation key. If it somehow gets called by a null one, it won't do sad things. And then what we're doing is we are creating another listener. So we're taking the language that our application has selected and the key that we got from the previous method, the previous listener, and we are listening for translated text to the language we have configured. And this is a model you will do a lot, is as you build out this kind of stuff with the real-time database, the subtrees that you care about will change a lot, will move around based on events in your application. And the listeners themselves are actually very cheap to construct. So it's not unusual for a more feature-rich application to have hundreds or even thousands of listeners. Sometimes they'll be changing changing on the second or minute. They're very cheap as part of the way the client library is constructed. So don't worry about creating a bunch of listeners. But try not to leak them. If you leak them out, you end up syncing data you might not want, and you might be sad then. So then what we are doing with our listeners, we're adding a value event listener. And the value event listener will, so the previous one listened for when any children got added to the node just below. This one is listening to changes in the state of anything in that subtree. And whenever anything in that subtree changes, we're going to get a snapshot of the whole subtree sent back to our method. And what we do here is a pretty simple thing. We get the data out of the snapshot as a string, and then we pass it to the platform, the Android native text-to-speech. So let's go ahead and see if this runs. Let the APK install. It's getting faster. It's funny how that happens. So now what we can do is we don't actually have any of our translation stuff written yet, but I can totally pretend to be it. So I'm using this database viewer to add it, and we need a fake key. And then under that, we are listening for, what's currently selected is English. And then, hi, everybody. And hey, it appeared right there. which is pretty cool. And it's a value listener, so it'll respond to changes automatically. So I can even change this, and it'll change pretty fast on the client, which is pretty cool because this one's going over wired Ethernet, and that one's going over conference Wi-Fi. So it moves pretty fast as a round trip to the Firebase servers, which is pretty neat. OK, so now we have our client, which works, and can both read data from Firebase as well as write it, or can write data to Firebase, the metadata about the upload and the binary data itself. And it can also respond to changes in the real-time database. So, like, we're done, right? Not really. I typed the translation myself, and as I mentioned at the beginning of the talk, I'm sadly very monolingual. I'm ashamed. So I can't actually implement this by typing myself. That, and I would get pretty tired after a while. So this is where we can pull in other cloud platform services and other fancy serverless stuff, new shiny fun things, to make this work better, to actually implement the translation features. And we're going to do that in, of course, the trendiest way possible today. We're going to be adding machine learning. But I don't have time to train my own model or anything, and I'm not very knowledgeable in that area anyway. So I'm going to take advantage of some of those pre-trained machine learning APIs, which are really just kind of a REST API that you can send requests to, and they will do some work for you with magic, and then you get back some slightly different data that is magically more useful to you. Specifically, we are going to be using the Cloud Speech API, and the Cloud Speech API will take our audio recording from the app and then transcribe it into text. And it supports a whole bunch of languages, which is great. Then we're going to take that transcribed text, and we're going to send it over to the translation APIs, which will translate it into all of the languages that our platform supports, and then we're going to pass that back to the client so it can speak the language that the user has selected. At which point, it seems like the problem is already solved. We can just wire up those cloud APIs to the client, and everything will be great. Kind of. Because it turns out that if you put something into a mobile application or on client side, especially something as valuable as an API key, or if you're writing a game like the cheat detection code or something like that, someone is going to reverse engineer your mobile application, get that stuff out, release it to the world on some forum somewhere, and then you will be sad because you will run out of quota on the speech API, and your app will stop working, and you'll have to pay for someone else's use of your speech API, and that's sad. So, mobile applications have a lot of secrets, is what I'm saying, and you need a way to keep that secret away from the prying eyes of would-be not nice application users. We also have to deal with the case of CPU load. So mobile devices are great. They've become faster than ever. The CPUs are ridiculously fast now, but the batteries are not much bigger than they were several years ago. So I could put the models on the device directly and do a lot of this heavy lifting on the mobile device, but then my phone might be hot while I'm using it, and then the battery will die fast, and my users will be sad, and they won't use my app. So we also want to be conscious of the amount of CPU time. And also, I'm building an Android app in Kotlin today, but we might want to support multiple platforms. We might want to write an iOS app, which has a very different development model. And rather than hire 2 teams to write our app in parallel and try to somehow keep everyone in sync and get feature parity and some kind of design parity, I'd like to be able to do as much of the stuff with a single chunk of code as possible. And there are different solutions for this. There are frameworks for taking code and putting it on multiple platforms. But there's another way too. What we can do is, traditionally what we might do for this is spin up some servers and push all of this work to the cloud. Spin up some backends that do the heavy lifting, that broker our communications with the APIs and keep the API keys secret and away from our users. But if our application is successful, we're going to end up exactly where we didn't want to end up, managing a whole bunch of servers. And I'm working for a hipster startup company. I want to continue moving fast and focusing on the front end and the user experience for my application. And at Google, we've been doing serverless for quite a while. Way back in 2008, we launched App Engine. And we've been doing a lot of serverless stuff for a very long time. And we've been doing a lot of serverless stuff basically internally for even longer. And over the years, we've learned a lot about different serverless technologies. And that's where new stuff becomes available to everyone. And specifically, one of the newer things I've been using I guess it's not that new anymore. It's getting close to a year old now. But it's really fun for dealing with problems just like these. It's cloud functions. So because we're just doing a small amount of brokering and have a small amount of secret data and not really that much complexity in the cloud, but potentially big spikes of scale, cloud functions is a great way to solve our problems. So let's switch over to another language, away from Kotlin land, away from Android Studio, and let's bring up IntelliJ, and let's write some cloud functions. So this is kind of where you would start if you were writing a cloud function that used this stuff. We have a bunch of dependencies we're pulling in. Yay! Cloud Speech API, Cloud Translate API, all of our different API keys for making those calls, and one little boilerplate method for handling the different representation of language codes between iOS and Android. But we get started. We have very little boilerplate code, which is kind of cool. It's a neat place to start, because you can basically start with an empty file, which is something you don't see a lot on platforms these days. So the first thing we're going to be doing is we are going to be creating a JavaScript function, because it is Cloud Functions, right? And this function is going to be, when you use Cloud Functions with Firebase, there are a bunch of different events you can respond to. And the Cloud Function will be called whenever those events occur. These could be like webhook events, like you have a URL, when it gets hit, the function runs. But there's also some that tie into different parts of Firebase directly. So for this one, I am writing something that is triggered when there's an event on the real-time database. So it's a database trigger, and then I give it a path, a subtree, that I care about. So whenever something happens on a path that matches this query with a wildcard, the function's going to get called. Specifically, whenever something happens on the uploads node with any identifier, it's going to call this function, specifically when it sees a write event. And writes will include changes as well as new creation. And then it's going to give me an event payload that contains a bunch of goodies. The first thing I'm going to do is unpack that event payload and put it into more convenient to use things. So the payload's going to come with, for example, the language and the sample rate and all the other stuff that's within that node. So what I'm doing is I'm reading the object that got passed into the function from the database. The next thing I'm going to do is take that data and remunge it into a slightly different format. So I'm going to take it from my mobile application format that I push to the real-time database. I'm going to change it to a format that I can send to the speech API. So I'm unpacking bits from one format, packing them into another. And then I'm going to point the function at the recording where it lives in cloud storage. So I don't have to actually download the data, like I don't have to pass it through or anything like that. I can just point it to the location I've already uploaded it. Then I'm going to run my recognize event. And that's going to give me a promise. So when that returns, then I will have the recognized transcribed text. I'll take that, and I will get another reference to a location in the Firebase real-time database. And I'm actually interacting with it through the admin SDK, because I'm running in a trusted environment, which allows me to bypass a lot of the security rules and stuff like that. Because this function is in a trusted environment, I'm giving it access to all of my real-time database, which is not a pattern you have to do, but it's something that can certainly be convenient. So that's why I'm using admin ref here, just as out of convention. And then I'm going to write the transcribed text as well as the language. So with that written, it's going to write the transcription to the real-time database, and I can signal the next thing. Oops. So this is where the pattern I use a lot when I'm using Cloud Functions to solve these problems. I can chain them together. So I've just written a transcript down, which is not yet translated. It's still in the original source language. But what I want to do is I want to hear it. I want to have an event that I can trigger it to send it to the translation API. But I don't want to have one big monolith of code. I want to break it into pieces. So what you can do is you can have Cloud Functions that kind of chain together. Either they will send an event to the next one directly, or in this case, I'm sending an event through something that changes in the real-time database. So this is another write event handler on the transcripts node. See, where was I? C6. Pasting in another snippet of code. So what this one's doing is it's doing the same thing we did above. I'm going through and I am unpacking the data, and I've hard-coded the languages that my application supports. And then what I'm going to do is I'm going to do basically the same thing I did before, except kind of like a promisified loop. what I'm doing is I'm mapping through all the languages I support, and then in parallel, I'm sending a request to the translation API for all of the languages I support simultaneously, because why do them serially? Why wait? There might be some client currently using that. And then, for each one of those, if the translation is successful, I'm going to write the successful translation to Firebase real-time database. Currently, I drop the promise on the ground if it fails, but I could put an error handler here, like a catch, that would write an error event to the real-time database. So at the end of the function, because I just forked off a whole bunch of promises, I have to add promise.all to wait for all of them to finish running so I can finally exit the method. If I don't do this, the function will exit immediately, or maybe it'll never exit. It'll exit when it times out after like 60 seconds. So you want to make sure that you clean up all your promises when you do this and return an individual promise that terminates, that reaches the state transition at the end of your actual work. Otherwise, you can end up with unusual behavior because promises is crazy like that. It's still a language construct that I'm like kind of using effectively, but it is powerful. So let's go on back onto the slides. Boop. So at this point, I would deploy that Cloud function. I've already deployed it ahead of time to save a couple minutes so we can spend more time on the fun demo. But this is basically what it would look like. You use the command line interface to deploy the function. It's going to push up my functions to Cloud Platform, and they will be there ready to serve requests. If it has a webhook, it'll also tell you what the address of the webhook, the web trigger is. So with that done, let's all play with the app together. So I'd like all of you, whether you're home on the live stream or here in person, if you have a laptop handy or a mobile device, get it out, go to this URL, and turn the volume up all the way to the max. That'll make it more fun, I promise. And in the meantime, what I'm going to do is pull up, well, I'm going to go to it myself too, to show you what's there. You can pick a language on this web interface, a language you would like to hear me try to translate text into. And then I am going to write data to it from the mobile application. So let's see if this actually works. I'm going to attempt, while that's happening, I'm also going to show you the real-time database as it happens. So we'll watch the real-time database so we can see the function executions occur while this stuff happens. So I'm going to say something. Hello, world. I say that a lot during this talk. And hey, we saw the upload get written. We can see all the metadata there. The Cloud functions are now running, transcribing it. It is transcribed. Hey, it transcribed it to text. And now it is translating it.
Hello, world.
Ooh, I hear a bunch of languages picked. And we see that's translated in all of the different supported languages. And I can select a different language up here. I can even try and speak a language I don't speak. I'm going to try that. So I'm going to pick Japanese. Let's see how successful this is. Ahoya gozaimasu. So it went in, it uploaded again. We'll see if it successfully transcribed it.
Good morning.
Hey, I actually said something in another language. Yay, I did. Sometimes it translates to something else. So, did anybody pick a language other than the ones I showed on stage? A few hands went up. Did it actually successfully translate into those languages? Did it kind of make sense? Thumbs up everywhere? Wow. I guess I give it very simple phrases. Sometimes I'll try and speak something more complex and craziness will come out, which is pretty fun. But it definitely does stuff. So, what have we accomplished in the last 40 or so minutes? We solved a problem that I encounter in my daily life in the way I solve all of the problems in my life by writing a mobile application. We wrote it in Android with Kotlin, which is pretty cool. I love using Kotlin on Android. It's so much nice. It's so much nicer than Java. I love Java too, but Kotlin's a good fit for Android development. And previously, I might have done something like this, where I had to spin up a bunch of compute nodes. And this may be where, if I had taken this application and moved it further along in its life cycle, I'm probably going to end up spinning up compute nodes to do more development on certain parts of the back end. But it's certainly more fun to have an existing application that's working to start from before I start optimizing different components, using different training sets, maybe writing my own translation models, or actually doing the translation from audio instead of from text, which loses some of the resolution. And I presented a different way of accomplishing that fact and getting that prototype out the door. We took Firebase, we took a few of the backend components and a few of the client libraries and hacked up an Android app pretty quickly in not that much code. And then we wired it up to Cloud Functions so that we could use a couple pre-trained machine learning APIs so we could move quickly. So now this is where I'll encourage all of you. I showed you my favorite recipe for hacking out mobile apps to solve problems in my life. I encourage all of you to give it a spin. There's a free tier for all of the Firebase stuff, and you can build a lot of these things. I think all the translation APIs and stuff, like that's the cost for those. There's free tiers for those as well. So you can get this working pretty quickly. So go build cool stuff. So we have a little time left if anyone has questions in the next 4 minutes. Also, if you're interested in running this yourself or giving it a poke or seeing the web application or an iOS version of the same app, they're all up there on GitHub. Or rather, that goes back to my webpage. So it goes back to a webpage, miming.com/z2a. And there's slides. All the goodies are up there. So any questions? None. Well, if you have any questions, I'll be hanging out. Just come poke me in the hallway, and we can chat about serverless mobile application development and cloud APIs and stuff. So thanks so much for spending part of your Friday with me. Have a great rest of your conference.
Okay. Good morning, everyone. Thanks for joining us for one of the last sessions today on Devoxx. Thanks for being so numerous. It's always fun to see. Today, me and my colleague Mario, who sits over there, who will join me in a minute, we're going to talk a bit about image recognition, how you do that. We developed a product that you can use to identify clothing. Maybe you saw it. We had a booth on Devoxx this week on the exhibition floor. And we're going to tell you a bit about how we developed the deep learning network and how we developed the interface to work with it. So my name is Ben Vermeersch. I work for InfoFarm, part of the Explore group. We specialize in deep learning and big data and AI stuff. And Eynde, they specialize in all things web and Adobe, but Mario will probably talk about that a bit more. So over to the image recognition part. How do we do that? How do you work with image recognition with deep learning? So what have we built? Well, the first question was, can we build something that can identify clothing? So based on the images that are feeded into the computer, they wanted to see what's on the image. Is it a suit? Is it the t-shirt? Is it the blazer? What color does it have? Does it have long sleeves, short sleeves? Is it striped or not, or plain color? So you wanted to be able to identify all of that based on the imagery that we got in. But when we built that, we noticed that it was also very suitable to build recommender systems because when you can identify images and see what's on there, you can use that information as well to identify similar images and recommend those images to users. So that's what we've built. We've built a prototype, and in the end, we've built something that can be used in stores and is actually used in stores right now with a gesture interface that was developed by Eynde. Before I get into the specifics of how we built it, maybe it's a repetition for some of you, but I don't know who attended all deep learning talks this week, but a bit about deep learning. Deep learning actually is a special kind of machine learning. We all know the traditional machine learning, so what's the big difference? In traditional machine learning, say, for example, you want to see if something is a car or not a car. In traditional machine learning, you have to extract all the features that identify something being a car by yourself. So you have to write some logic to see, okay, a car, it has 2 tires, and it has some windows, and it has a trunk, and I don't know what else. But you have to extract all those features from the imagery yourself. And then you can use those features and build a classifier system saying this is a car or not a car, or this is a car, and this is a truck. The big difference with deep learning systems is that the deep learning systems do the feature extraction for you. You just feed it with a bunch of examples. In the case of images, you feed it with a bunch of cars or trucks or cars or not cars. And the network itself, it tries to extract features from the imagery and in the end classifies those features into something being a car or not a car. And we did the same thing for clothing, but you can do this for any type of object, of course. So a neural network, how does that work exactly? People always say neural networks, they try to mimic the workings of the human brain, and you train the human brain to recognize objects. So when we think of brains that still need to develop, we think of babies. So meet Seb. This is my son. He's about 1 year old now, and he's nearly my most advanced neural network that I've trained to date. My wife doesn't really like me calling him a neural network, but yeah, what gives. But my son actually is a neural network in itself. So my son, he really likes toys and balls. So what he's really good at right now is identifying something being a ball or not. So how does it start? Okay, my son, he sees a lot of balls. So he knows, okay, this is a ball, this is a ball, this is a ball. And then he a pattern emerges from all those images of balls, and he sees, okay, a ball, it is round. So I know that first thing is a ball, and the second object, that's a ball as well, because it's also round, and the third object is a ball as well, because that ball is round. But then my son, he wants to play with the ball, and he tries to pick up the last ball, and he notices, okay, this ball is kind of heavy, and I can't throw around with it, and when I kick it, my feet hurt. So he gets a second example of something not being a ball. And if I say enough to my son, okay, this last green thingy, that's not a ball, but that's a watermelon, then my son will learn, okay, large, heavy green things that are round are not balls, they are watermelons. And you do the same thing for training neural networks on a computer. So you feed it lots of images, lots of examples, and in the end, the system learns what it's fed and tries to extract features from it, and it can detect what features belong to which labels. And we did the same thing for clothing. So we gave a lot of images of clothing to our network and said, okay, this is a t-shirt, this is a blazer, this is a suit. And in the end, our system was able to recognize clothing. And we used some special kind of neural network called a convolutional neural network, which actually takes small parts of the image and tries to extract features from it. So it starts by, for example, using the left outermost pixels 4x4, and then he scans the entire image, and he goes along with it, and it builds a new image from those small features. So in the first step, you will probably detect edges and small objects and lines when you go over it. And in the end, you add a second layer and a third layer, and you do it over and over again, and then you get lapels and buttons and really identifying features. You can do the same thing, for example, with faces, detecting eyes and eyebrows and mouths, and in the end, trying to detect what mood someone is in, if he's happy or not. Same pattern emerges there. So that's a bit of how the network that we used works in the background. So how did we train our model? Well, by feeding it lots and lots and lots of images. We actually used approximately 300,000 images of labeled data saying, okay, this is this type of clothing, it has this kind of pattern, it is this kind of color. And we used a stack of Keras for the modeling with a Theano backend. And sorry to say, but that's all Python-based. I like Java as well, but for now, Python is most suited to train and work with neural networks. You also have something called deep learning for J, which can actually use Keras-built models as well. So we're looking into that, but there's still a performance hit. So for now, we still stick with Python. But I think everyone will understand all the code examples as well. We started just doing CPU-based training, but we ended up buying just one performant GPU card, because that goes a lot and a lot faster. So if I can give you a hint, if you get started with this, invest in a good GPU card to do your training, because it will speed up your development cycle 100-fold or 1,000-fold. So over to some code. How do you create a model in Python? So the first thing you do is just you create a new model. So that's the initialization of your model there. And then we say which shape we will feed into the model. So in this case, we had images of 128 by 128 pixels with 3 layers, so a red, green, and blue layer. If you have only black and white, you only have one. And then we add different layers into the network. So the more layers we have, the more features we can distinguish. Of course, this doesn't necessarily scale, or is useful to scale into a bunch of layers. I think we ended up only using 3 or 4, because every time you advance a layer, you use more and more of your image or more and more of your features. And in the end, you end up with all your image, and then it just starts to get confusing for the network. So we had a bunch of layers, so the convolution 2D layers that are used in a convolutional neural network. And in the end, we add a classifier layer, a logistic classifier that uses the features that come from the other layers to say, or to classify this is this object, this is a suit, this is a blazer, this is a t-shirt, this is a dress. And in the end, you just compile that model. And then you have an object, a model object, that represents the hierarchy of your model, the layout of your model, that you can start training. So how do we train that model? By feeding it lots and lots of images and lots of labels. But how do you do that in code? So we take the model that we previously initialized, and then we use the fit generator method in this case. Why a generator method? We can also use the regular imagery, but using a generator, we can create more and more images based on original images. So what it does is it shifts and it rotates and it adds some distortion to the images in order to get a better trained model, because obviously the new images that you're getting in aren't always that clean. So that's an easy way to add more and more data. So we feed our RGB data from our image to the generator to generate more and more images, and the labels associated with that image. So for example, if I have an image of myself, I say, okay, this person has a blazer and it's blue and it's plain, for example. And then we also have some configuration, and in the end, a callback method. So what that callback method does is save your model to disk. Well, in our case, you can do other things as well. So this means that in the end, your trained model is persisted and it can be reused as well. You can load it in, load it from disk, transport it to other systems, even put it on mobile or something like that, and start working on it further. You can even use it as a layer in other models as well. So that comes in handy when deploying to a server, for example. And after doing this for thousands and thousands and thousands of images, and after a couple of hours and a couple of days of trial and error with fixing the model, you end up with a trained model that you can use to categorize images. And categorizing images is just plain and simple. You open up your image, and you take your trained model, say, okay, predict the classes for this new image, and then the model says, okay, this new image that I get in is an image of a t-shirt, and it's white and it's plain. Or it's an image of a dress, and it's a long dress, a blue dress, and it has a floral print, for example. So it really, it looks quite simple. Of course, there goes a lot of tuning in developing the right kind of network and selecting the right kind of images, but I'll get to that later. But just code-wise, it's actually real simple. And Keras also takes a lot of the conceptual modeling out of your hands. So in the end, it's not as hard as most people think it is before starting with it. So we can categorize image, and this is, for example, the output of one image that we had. So if we feed in this image of this fine lady here, and it's entirely unreadable, but it says, okay, this is a dress, that's the top one. It is black mainly, and it has a floral print. The cool thing here is that you don't only have the first bet of your model, but also your second and your third best bet. And optimizing for 100% accuracy on the first bet is really, really hard. But you should also look at accuracy in the first 3 bets of your model, because that can also be used in products. For example, if you want to use this to automatically categorize imagery, or you have a new catalog in your store that you want to put in your system, you can use the system, and the bulk of images will be right from the first try. But the things that you're uncertain of, you can feed to a manual operator who can check it, and you can also present him or her with the second and third options that your model came up with, so to make the selection easier. So now we've built a model, and that model can detect what's on an image. So the next thing we wanted to do is use that model or the features of that image to recommend similar clothing. So how do you do that? How do you tell your model what is similar and what is not. One thing you can do is train a model separately for detecting similar items. So it will work kind of in the same way, feeding two images and saying, okay, these images are similar, and then the model detects what are features of similarity. But what we did is kind of a different approach. We used a traditional model of nearest neighbors to detect similarity in images, because the model, it comes up with a bunch of features. I think 1,000 something features that we have for every image, and those features that can be used in a traditional way, using traditional machine learning and recommender systems to do recommendations and find similar feature vectors. So what we did is we just got rid of the last step of the model you saw previously in the slides, which was the classification step of our model. And if you get rid of that step, you just end up with the raw features of that model. And we can use those raw features and put them in a feature matrix. And then whenever we get a new image that we want to find similar images for, we just get the raw feature vector of that image, find the nearest neighbor or the most similar feature vector for that image in our catalog, and then we have a similar image based on the catalog that we already trained. So how do you do that? You take, the truncated model is the original model that we had for the classification with the last layer omitted. That's a truncated model that we created. And we use the same predict method to get the feature vectors now, not the labels, but the feature vectors for the image. And then all of those features, they go into a feature matrix. So for example, you have a catalog of 1,000 images, you have 1,000 feature vectors in a matrix. And then we can use something called the SciPy library in Python to just build a tree and use that tree to find the nearest neighbors. So it's as simple as querying that tree with the new image features for a new image that we take into our systems and say, okay, I want k nearest neighbors. So for example, 10 recommendations, and then you get 10 new images in your system. So to give you an example, the same lady here, if we feed that into our catalog, we get these recommendations. If we get the 8 first ones, so we see we all get dresses. They all have floral prints. They all have more or less in the same color. Of course, the lady itself is also taken into account a bit, so the blonde hair counts as well. But yeah, it's still a work in progress. So what have we learned by doing this? First and all, use your GPU. It makes your development cycle a lot faster. You don't have to wait for 3 days for a new model to train. The last percent or the marginal wins are really hard, as in every machine learning model. So you will first have some quick gains, but then really specific cases can become quite hard. And a quite important one is that the only thing your model will know is what you learn it, what you train it for. And you have to be really careful not to introduce bias into the model. I'll give you an example. If, and that's actually the case, for example, for blazers, every blazer in our training set is a blazer with a closed button. Which means if I take a picture of myself with a closed button like this, the model will detect, okay, this is a blazer. But if I take a picture of myself with my blazer like this, then the model will think this is a cardigan, because the lapels in here are really cardigan-like, and cardigans are all opened up in our feature set. So if you want to detect both opened and closed blazers, you will have to feed in imagery of both opened and closed blazers. Because this is the most distinguishing feature for a blazer. The same goes for suits, for example. The only way to categorize something as a suit is when you wear a tie. If you don't wear a tie, it's never a suit. It's because everyone wearing a suit in the training set had a tie. And the hard thing, and that's a great distinction between deep learning and the traditional machine learning, is that the deep learning model, it chooses the features itself, and you don't really know what those features will be. Okay, there are methods to see what the features are. You can use deconvolutional neural networks to visualize them even, but still, the training set is really important for the outcome of your model. And the last thing, indexes in pandas, it's a data frame library in Python. They're really, really hard to work with. So I still prefer Java over Python, even after this one. So now we have a fully functional recommender model, but of course, yeah, we're kind of backend guys, so we didn't really know how to build a nice interface for this. So we contacted our colleagues from Eynde saying, okay, we have a very cool model that we want to use in stores, but we don't, yeah, you have to take pictures, so you have to take some distance from the screen, so we're looking for a cool interface to work with to put in stores. And that's what Eynde has developed. So I'll leave the word to my colleague Mario to talk about the interface that we built before this model.
All right. Hi, everyone. Everyone in the room and everyone watching us on YouTube. So yeah, my name is Mario van den Eynde. I'm a web architect over at Eynde Media Foundry. We are everything web company, and we also do Adobe Experience Manager. But I want to talk to you about how we came on building the whole front end and pieces of hardware that InfoFarm used to build the whole experience. But I want to start off with this guy. If you don't know who this is Tony Stark. Tony Stark is a billionaire, philanthropist, and he's also Iron Man. When I first saw the first Iron Man movie, I was fascinated by the technology that he had. Now, I know this is not real. I know man cannot fly in suits like that. But he uses very advanced technologies like holograms. So for example, if you look at this, he uses his hands, he uses gestures to interact with content that is floating in midair. And I was actually wondering, how can I achieve the same experience using hardware that is available for me? Now, I'm not a billionaire, so I can't buy all this stuff. So I wanted to find a way that I can build this myself, affordable, with the technology and the scripting languages that I know. So here you have another example. So he uses gestures to rotate stuff and zoom in and zoom out. So I wanted to ask myself, yeah, how can I, for example, represent a click? If I see things floating in front of me, how can I select things? How can I move things? How can I navigate through content that is actually not touchable? So the question was, how can I achieve this? And using programming languages that I know, and what's the hardware available? So I tested a lot of sensors, all of them from webcams to version 1s, version 2s of hardware devices, motion leap hardware devices. But one of them stood out above all, and that was the Microsoft Kinect, version 2, not version 1, and the development kit. That piece of hardware did actually everything that I wanted. Now, what did I want? It measured up to half to almost 5 meters, so that's quite amount of distance. It can track up to 6 bodies, so if 6 people are in front of the camera, he can detect, oh, there are 6 people in front and that I can interact with. Furthermore, it can track up to 25 joints, and that is very important, and you'll see that in a later slide, why that's very important. And you can see them on the right. From all the way to the head, all the way to the feet, every joint can be detected. So that's very important. It can also track the hand state. More on that later, but also, yeah, I want to know where my hands are in a special place and time. Also, you have a unique skeleton ID, which means that every person that's being tracked stays or gets the same ID every time. So he knows that you are person A And if you move to the left or the right, he knows that you are still that person A moving. It goes up to 30 frames a second, which is more than our eyes can see. It can measure depth, which is also very important. So I was already thinking that I can, if it can measure depth, I can move things in 3D space. And it does face tracking and emotions. Now, I haven't tested this yet, but in a future project, this will come in handy. So basically, when I saw that, I was like, yeah, I need this. So I saw it, I bought it. We currently have 4 at the office. That's how addicted, at least I am, to this piece of hardware. So the setup is actually very basic. So you have the piece of hardware, the Microsoft Kinect. We have a very high-end desktop computer to hook it up to, and then a Samsung display that we can put in portrait mode so that we can actually see our whole body. So this is all very basic and all very affordable. So the hardware, yeah, okay, checked, we bought it, we hooked it up, it worked. What was the next step? Yeah, how do I get the data from that little box onto my, to the desktop and into my application? So yeah, how do I get that data? The only programming languages that I know is HTML, CSS, and JavaScript. I don't know C#, I don't know .NET, I don't know Java or Python or anything else. It had to be JavaScript. So front-end wise, yeah, this was a no-brainer for me. I use this day in, day out. So we used ES6 with a Webpack bundler, a React front-end, and a Babel transpiler. So we had this off the shelf. This was set up in 5 minutes. And then I started thinking, okay, what do I have to use as a backend? Since it's JavaScript, I had to use Node.js. I know Node.js. But then there still wasn't a connection from my device to the Microsoft Kinect. So I had my fingers crossed and I searched the web for a Node module or an NPM module that would actually do this for me. I didn't think there was already someone in the past that was crazy enough to actually do the same thing, but yeah, thank God there was. So there are on the web 2 GitHub repos. Actually, the second one is a fork from the first one. But we used the second one because it uses a different edge. In this case, edge.js. Now, in short, what's an edge? It just connects 2 nodes. For example, you have Node.js and a .NET. You have 2 processes, and it gaps the bridge between the 2 of them. So your Node.js environment can call .NET functions and vice versa. So in our case, it had to run a C# commands from Node.js, because if you check out the repo, you have access to the code, and it was in C#. So, all right, fingers crossed it worked, and eventually it did work. So I had my hardware, I had my setup, I had a Node module that hopefully worked. Awesome. So I spent my days figuring it out, saw the first sample application, and this is actually the only pieces of code that I had to create my Hello World app. So what you see here, if you are familiar with web technology, you import your Kinect 2, you instantiate it. If the Kinect is found, you see all the lights go on, you see all the output. For example, the console open, it says, okay, your Kinect is connected. And basically what this piece of code does, it just outputs JSON. JSON information to the console, and after 5 seconds, the application stops. And if you get the console log that lists all the bodies, then you know your connection works, and now it's just a matter of find a way to get that data into your application. So if you look at how this JSON looks like, so this is body index 0 up to 5 or 6. This basically is tracked, the tracking ID, it's unique, as I said earlier. And then the hand state. The hand state, it can go up to 4 states. So when it's closed, a lasso, not tracked open, and unknown if your hands are, for example, out of the field of view. Now the lasso tool, that's something different. I didn't know what it was. I had to Google it also. But basically, a lasso tool is, if we're all familiar with computers, of course. If you have the little index that goes like this, basically the lasso tool is adding a second finger. Now, why is that? Basically, because the device measures depth, one finger isn't big enough to bounce the rays of light off. So you have to use a second finger to actually see the state of the hand. So that's basically it. And then you have all depth X, the colors, the cameras, orientation. It can detect if your hand is like this, your head goes left to right, stuff like that. So now this was just basically finding the right coordinates to do the math with. So the hardware, check. Getting the data also worked. Now creating an awesome app during a sunny vacation in Italy. So while my girlfriend in the next room was packing all of the bathing suits and slippers, I was packing my Mac, my iPad, my everything piece of devices that I need, and I was up and running. So basically what the idea was, I wanted to create an airplane in the browser that I could control with the Kinect. So basically what this means is if you stand in front of the device, I asked my little niece, like, how would you portray flying an airplane? And immediately she goes like this. So you have 2 wings. So okay, yeah. So I was already thinking, I have these joints. I can measure the joints. And how would you go up? And she bent her knees. Okay, and then the airplane went up. And then the next issue arose, yeah, how do we make it go down? We cannot float yet into midair. So that were things that I need to tackle. So the steps I need to take, I had to learn 3JS. 3JS is a 3D library. It's very powerful, but I had to learn things like geometry, lighting, how to load external objects, how do cameras move and interact. So I downloaded an ebook and started reading. The next thing is, how do I get the data from the Kinect into the application? Because now it's just still running on the back end on a separate server. And how do I map my body that's actually in the physical world? How do I map these coordinates to the coordinates in the digital world? These were all things that I need to tackle to actually make the plane go up and down, left and right. So putting it all together, yeah, I had to debug, basically. I had to draw myself as a skeleton on a canvas, all right? Next, I had to place an airplane into 3D space. I just downloaded somewhere an object of a little airplane, placed it in there, and if it showed up, I was already happy. And then I had to make it fly. Those were actually the 3 steps. So this is what it looked like. So as you can see, this is actually skeleton data. Every red block is actually my head, my shoulders, my upper torso, my waist, my hands, my legs. My feet are not in there because they're not important at this moment. But actually, the state also from the hand can also be checked. So green was open and blue was closed. So basically, this is how this looked. So this is me standing on my terrace on our holiday home in Italy, surrounded by tens of other people I don't know, looking at me like, what the hell is he doing? My girlfriend sitting next to me reading a comic book because she's addicted to comic books. And I was like, yeah, it worked. And she just lowered her comic book going like, what? What are you doing? And then I explained everything to her, how this works, and yeah, she thought I was cool again. So basically, how was this made? Actually, if you narrow it down, it's very simple. So I had a local host running on a separate port. that was connected to the device itself, giving me JSON data. And every time a body frame event occurred, the device just spat out events called body frames. Every time that event occurred, I just passed it along a socket, and then I had the front end listen to that same event on the same socket, and then the data would be passed. It's very easy, actually. So now I had a bridge between my back end to my front end. The data was coming in, so now it was just a matter of math and JavaScript. So this is actually the piece of code that gets the data in. I clear my canvas because the canvas gets removed and filled in with all the red dots. I loop over all the bodies, and if the body is tracked, at this point only I was crazy enough to stand and do things like that. So there was only one body at this point. I created the little red blocks, and then I have a method, update hand state, that would control if my hands were closed or open, and then the elbow state. And the elbow state was actually the most important function. Because what I did was, if I stand like this, I had the coordinates of my elbow on the left and on the right. And then I would measure the distance between this and my center point, like this. So if I went like this, the plane would go that way, if not the other way. So that's basically the way that I tackled this. And this is actually how that looked like. So if my elbows are practically on the same line, we're leveling, the plane just goes straight. If my left elbow is higher, then we go to the left, otherwise we go to the right. And we output it to the screen. And if the jet is loaded, we just rotate his Z position, and we're gone. Now, we had everything. I tackled everything. It was a proof of concept, and yeah, it worked. So how could we translate everything that we know into the clothing analyzer? Yeah, again, what is a gesture? How can we navigate through the application? How do we define a swipe? And how do we translate all of this to code? For example, a mouse click. A mouse click we can interpret in many different ways. For example, do you go like this? Do we use the whole lasso tool? Or do we implement something that if you hover long enough over an element that's on screen, we would show a little indicator. And if the indicator is fully filled, then a click would occur. Or would we go like this? And if a fist, if your hand is open, make a fist and open again, is that a click? Now, we had so many different opinions that basically the only thing we could do is ask people to come stand in front of the camera and just start doing things intuitively or naturally. And basically the first result was something that I call the Beyoncé. Every person, and literally every person that tested the application, they went like this, really. So they asked us, how do we click? And they all went like, really like this, just to tap. But then we explained, yeah, it's not working like that. So we implemented the whole circle thing if you hover long enough over an element. So yeah, the version 1, we know how to code the gestures. It works. So we measure the distance from one point relative to another point. But there were there were a lot of issues actually. Is the UI intuitive enough? So practically not. The app started lagging after a couple of minutes, and really, really lagging. At a certain point, it would ultimately freeze, and we had to reboot the whole application. And the third-party libraries that we included couldn't be wrapped into an Electron app. If you don't know what an Electron app is, basically it's a wrapper that enables you to create web applications and build them as a DMG or an XA or something like that, as a really standalone application. And inside, a Node environment gets spawned and a Chromium environment for your front end. But yeah, of course, we built a version 2. What we did was we connected the Kinect to a separate worker JS, which was basically running on a different thread. It would still send the body frame information. We compressed the data image because it was full HD. It was too big, so we compressed it. And we were in control of the frames per minute instead of actually running code every color frame or body frame event. So we were in charge. And we had to rebuild the Kinect libraries that we used to a specific Electron version. This was actually the most time-consuming, and thank God for Google and Stack Overflow. But eventually it worked. We got it up and running. We made a standalone application, and it's still working today. So this is basically the setup of how the application works. We have the Electron wrapper. In the Node environments, services get spawned to upload photos to S3, and the worker.js to connect to the Microsoft Kinect. And there is an IPC main and an IPC renderer. Basically, that's the bridge between what the user sees and what's running in the backend. And you can send events over it just to ask data and get data synchronously or asynchronously. And then the Chromium web browser is basically a Chromium web browser that's just spawns up the HTML running the React application, and everything's up and running. So these are a few screenshots of early UI. You had to tell the application that I'm a male or a female. Once that was done, you get a little text that says this is how the application works. So you can swipe. So for example, we detect this hand position in time and space relative to this point, and if it was past that during a second or 2 seconds, you would swipe left, and this would swipe right. And then if the application took your picture, it was uploaded. Some magic thing happened in the cloud, and we get different versions back in a JSON array, and we just made it look pretty on screen, and then using swipe gestures, you can navigate to the next and to the previous one. But also, we had to know if the results were accurate or not. So the last screen was, did the results that you were given, were they accurate, yes or no? And after 10 seconds, the screen would just disappear. You jump back to the start screen, and the whole flow just starts over again. So basically, that's it. I want to thank my girlfriend for loving comic books when we were on holiday, so I can do cool stuff like this. The colleagues over at Eynde Media Foundry, especially Marco Lambrechts, who's actually the brain behind all of this for coding it, figuring out how the whole swipe thing and math. Laura de Winter and Astrid van der Hasselt, who are our creative geniuses, and everyone who tested the application. And there's one more thing. I started the presentation, or my part at least, with the whole Iron Man thing. He has one other awesome piece of technology, and it's called Jarvis. If you don't know what Jarvis is, I suggest you Google it. We are working on it, and maybe this is something very interesting that we can do next year. This is mandatory. We're hiring, so also Ben and I, InfoFarm and Eynde Media Foundry. So there's maybe one thing that I want you to see. Oh, that's big. Can you see this? Yes. This is actually a proof of concept that two students of ours did, basically using the same technology. You can configure your clothes, for example, a t-shirt, a hat, your trousers, and your shoes. Just by going like this, I want to select the row. And if you have selected a style, it gets mapped onto your body. These are all very low poly models, but if you have very detailed models, basically you can do just stand in front of a digital mirror or something like that, or even in your living room, and just try out clothes without even leaving home. So what they did is they embedded functionality to control the lighting, the size, stuff like that. And at some point, I even think there's something like a dress in there or something. Yeah, all right. So yeah. So this is Taz, our male model. So that at this point, you can already see that the lagging is occurring. So this is. So as you can see, it's a little lagging at a certain point, and it just died. So this is something that I worked on during my free time. A lot of cool stuff is happening in the future. So all right, thank you all for listening, and yeah, enjoy the rest of your day.
Ik weet niet wat de ruimte is. Zo.